Hi, this is an example problem from Chapter 22 on electric motors. Pause for a moment to read the question. So this shows an electric motor which is attached to a external voltage source. So it looks like a DC battery, 120 volts, right? It turns out that a motor can be modeled. If you look at this picture here, we've circled this thing in blue. We consider that the motor, and we can model that as two components, a resistor and a back EMF that are in series and also in series with the battery, the external voltage source. Below you see a real motor and how it works. We learned in Chapter 21 that when you have a current flow through a wire that's in a magnetic field, it exerts a magnetic force on the wire, and that causes the loop to have a force on it, causing a torque on the loop, which causes it to spin. Now, in addition to that, we also know that because the magnetic field is passing through the loop, that generates a magnetic flux. And if you think of the normal to the loop as being, say, okay, kind of hard to draw, but like there's your normal to the loop, right? And as the loop spins, this thing is going to go ahead and spin, going around in a circle. And the fact that it's spinning means that the amount of magnetic field that passes through the loop is going to be changing constantly. There's a constantly changing magnetic flux, and because of that, that creates a back EMF, this right here. And the back EMF always opposes the direction of the current. So it's almost like having a battery that points backwards in the motor. However, it depends on the rate at which the motor spins. If the motor spins really fast, then it makes a bigger back EMF because the magnetic flux changes quicker. And if it spins slower, then it has a smaller back EMF. Now, to solve this type of problem is pretty straightforward, because what we're going to do here is we're going to just go ahead and come up with an equation for the circuit that you see here. And we're going to go ahead and use Kirchhoff's law to come up with that equation. And any other motor, that is set up in the same way, just attached to an external voltage source or a battery, is going to, obey the same equation ultimately. So if we think about it, let's go ahead and start here. And we're going to go ahead and do a Kirchhoff's loop rule, just going this way all the way through everything and then coming back to where we start. So this is just to get the right equation here. Remember that when we go across a voltage, we got to use Ohm's law. And first thing we need to do is figure out the direction of the current. We know the current's going to go in this direction. And therefore, we can now go ahead and say that this is the plus side of the resistor, that's the minus side. The battery and the back EMF have already been labeled, and now we can go ahead and use the rule for Kirchhoff. So let's start going here. Oh, we got to jump across. There's an increase there. Let me just call this plus V. I'm going to call this battery, B for battery. We know what the value is. And we're going to keep on going. Okay, no change, no change. Okay, we got to jump across this guy. That's going to be from high to low. That's going to be a decrease. This is a resistor, so it's going to be a decrease minus how much? V equals IR, so it's going to be the current I multiplied by the resistance R. All right, we got to keep going. Okay, here's the back EMF. We got to go across that. We're going from high to low. That is a decrease. So that's going to be minus, and we're just going to call this E back. And now we have gone across all the circuit elements. We're back to start. So these things add up to 0. And that's the basic equation for a motor. Part A asks us, when the motor is initially turned on before rotating, and part B, when the motor has reached its maximum rotation rate, find the current in the coil. So again, E back depends on the amount of rotation that you have, right? So E back in part A is going to be 0 because it hasn't started rotating yet the instant you turn it on. Part B, when it reaches this maximum rate, then it's going to, you're going to have some back EMF, which is told to us there. To start, let's go ahead and just solve this equation for the current. and then we can use the same equation in A and B. So if we want, we can go ahead and write this as the voltage of the battery is equal to, let's see, we want to keep the keep E back here, equals IR. And finally, to go ahead and solve for I, let's switch the directions and of the equation, the sides, and divide by R. We're going to get voltage of the battery minus E back divided by the resistance. That'll tell us the current in the motor. So for part A, we've got no rotation when it is initially started up, so we're going to get a bigger current because no rotation means E back equals 0. So in this case, I is equal to VB minus E back. I'll write it down, then I'll just say that it's 0 divided by R. This is 0. The battery, 120 volts. The resistance, we're told, is 10 ohms. And this comes out to a current of 12 amps in part A. Now in part B, we're going to do the exact same thing, except now we don't have 0 E back, we have maximum rotation. And we're told that the maximum rotation is producing an E back that is equal to 70 volts. So we're going to have 120 volts from the battery minus 70 volts due to the back EMF, still divided by the 10 ohms. And when we put that into our equation, that is a calculator. Shoot, we don't need a calculator here. That's going to be equal to 5 amps. One comment I want to make about motors, it's interesting to note that you actually, when you have a motor that is working hard because it's trying to, do something hard that's hard to do, so it's hard for it to spin, you actually get more power. And that's because since it's a big load that the motor needs to achieve to spin, it doesn't spin as fast, and therefore there's less back EMF, which means you get a bigger current, and therefore you have more power. So it's interesting. It seems kind of counterintuitive a little bit, but actually you get more power if the motor tries to work too hard. Of course, if you get the motor locked up because you're trying to make it do something that it can't do, then you're going to get this big current, and that'll heat the motor up and probably cause the wires in the coil to melt and destroy your motor. So anytime that you're running the motor and it stops working, don't keep running the thing turned on because you might burn it out.